Hello, I'm Ranger Scott. I'm an electrical engineer, and for the past 5 years, I've been building electrolysis cells like this because I find them to be generally interesting and they integrate well into a lot of my projects. And I recently found out that the NASA Artemis mission is trying to do something very similar. They're actually trying to extract water ice from the craters in the south pole of the moon, and split that water into hydrogen and oxygen for the astronauts to breathe or to convert into rocket fuel, which I thought would be an interesting thought experiment to see if my cell would survive in this environment. And the answer is maybe, but I wanted to give some brief background first because plans have changed a little bit since the release of this video. But the current plans are that they're still trying to land on the moon by early 2028 here. As of writing, they just launched Artemis 2, which sent 4 astronauts around the far side of the moon. But I wanted to focus on the bigger picture of why. Why are we sending astronauts back? Well, NASA's page shows that Artemis 3 here has been rescheduled as a demonstration in low Earth orbit, as a competition between two billionaires, I guess, for bragging rights, to see which lander is going to be validated for the Artemis 4 mission, where we finally actually return 4 times the charm, I guess. But it's going to be in one of 9 landing locations here. These are all in the south pole of the moon. The main draw of this location is, of course, the permanently shadowed regions, where temperatures can drop as low as 250 degrees Celsius, so very cold in these permanently shadowed regions. And I'll link this paper in the description. They also have a very good visualization of what the temperatures are like in this region. You can see everything in purple and blue is very cold, under the 9-degree threshold. But the moon only has a 1.5 degree axial tilt, so many of these crater beds are just in permanent darkness, while the actual crater rims usually have a lot of light on them. Some of these are in perpetual light, so it's a good balance because you have these lit regions where solar works really well, and then you have these really cold crater beds where water could be present, water ice. So that creates a temperature differential of like hundreds of degrees in just a few miles, which is pretty crazy. But it's probably more like frozen sand, more like frozen lunar regolith, rather than an actual glacier. It's not like this. So, and we're not even sure if that's either. I mean, they say that the form, concentration, and distribution of water in shadowed regions is not known. Yeah, it's kind of up in the air right now, but I mean, it's cold enough that water should freeze there without being able to sublimate. That's why they're these cold traps. Yeah, I mean, for some context, the coldest temperature ever recorded on Earth was negative 92 degrees Celsius in Antarctica. And some of these craters are almost twice as cold as that. I mean, you can see here in this snippet from a NASA article that, I mean, some of these get negative 246 degrees Celsius recorded by the Lunar Reconnaissance Orbiter in these craters. So very, very cold. Normally, I mean, the moon doesn't have an atmosphere, so you can get the normal temperatures swing from 120 degrees Celsius down to negative 130 degrees during the lunar night. That's every 13 and a half days this happens. So you can see why that would not be very conducive for water to exist. And there's also this very good visualization of those craters and how the sunlight on them behaves. I mean, you can see in some of these craters near the South Pole here that they're pretty much constantly lit on the rim. But sunlight never appears in the actual crater itself. So that's why we're trying to get there. And that we think that there's water in these craters. And yeah, I mean, it's very cold. Some of these craters, I show here that like negative 273 degrees is absolute zero. So this negative 246 degrees figure, that's only 27 degrees above absolute zero. So I mean that's the worst case, but you aren't exactly going to waltz down there and get that water. I mean, it's twice as cold as Antarctica ever was. So yeah, Earth kind of has some rookie numbers compared to what these craters are capable of. Everything in purple and blue here is colder than anything that exists on Earth. So very cold. And of course, this prevents water from sublimating in the near vacuum of the moon's surface. But yeah, of course, it's probably more like that frozen sand I was showing, rather than any glaciers. So still very difficult to extract. Um, and plus that low pressure on the surface lowers the water's boiling point even further. So yeah, you can see that here. I mean, it's pretty much very little pressure on the moon's surface, so the boiling point of water drops to almost zero. If you put liquid water on the moon's surface, it would first boil due to the low pressure, which would force the temperature down, so it would actually boil, then freeze, and then sublimate away into nothing. Then if you're lucky, that evaporated water would come and settle in a crater like this, a cold trap, and freeze. Otherwise, it would just get blasted away by the solar wind, never to be seen again. So that's what we're up against. Crazy conditions, really high temperature swings because of the lack of atmosphere. And I did have so you can see here that the moon only has the exosphere. It's very thin atmosphere. So not much to protect us there. And these craters, I mean, that too, these craters are massive. I'm not saying that Shackleton would be our destination. There was 9 destinations possible. But I mean, Shackleton itself is 2.5, 2.6 miles deep. And the circumference is 1.28 marathons. So you could run one marathon around this crater and you wouldn't even reach the end. So some massive scales we have here and massive temperature swings, which makes this a lot harder. And plus, on top of that, you have a really healthy dose of radiation to go along with that. So yeah, crazy conditions. Very difficult to get to this water. What was this video about again? Oh, right, yeah, electrolysis. So the NASA page for Artemis 4 isn't very specific on what experiments we're going to be doing here. They say like a sample return, of course, but I mean, the goal is to make a living, to have like a base here, which water is going to be a very large part of. So in this page here, you can see that one of the goals is this in situ resource utilization, and that includes getting oxygen from the lunar regolith, the water in these craters, and experiments to make fuel from this. So, and this they do specifically, they don't mention electrolysis here, but in a page here from 2023, they talk about these in situ resource utilization experiments. And they talk about how they have 9 water electrolysis projects with 3 different types. So those are the proton exchange membrane ones, which looks like this here. This is one of their proton exchange membrane experiments. And then they have the solid oxide electrolysis. That one has to operate at really high temperatures. And then they also mention alkaline, which is mostly the category that mine falls into. Before I would talk about my cell, I want to talk about the current applications of electrolysis cells. You can see here that they have an electrolysis cell aboard the ISS. They actually have 3 electron style reactors. These have had some issues in terms of like maintenance and constant breakdowns, along with they had a spill once, which was funny because I dealt with a lot of these same issues during the development of my cell. They had to shut down and vent some stuff to protect themselves. But they have 3 of those electrons, like reactors. And then they have one of these Awuga cells, if that's how you say that. Funny name. Like glad they named it that. But these are these operate in 0 gravity, so they don't have gravity to separate the bubbles. So I was thinking maybe you could use like a centrifuge, and I think that's what they do use here to simulate gravity and to get some separation. But yeah, it's a pretty complex system involving the generation, separation of oxygen out, and then they send the remaining hydrogen to a Sarbitter reactor, a Sabitter. Excuse me for butchering that pronunciation. But I mean, you can see how many rabbit holes I could go down trying to research this video, and I got to get it out at some point. So, I mean, yeah, they recycle everything they can. But in general, most of the oxygen and water just gets sent up to the ISS and resupply missions. So, I mean, it's a supplement for sure. But there's also, of course, thruster designs that involve hydrogen and oxygen and electrolysis. Different designs of how to separate these gases rather than the centrifugal force that I show here. And then another interesting application of electrolysis are the Hubble Space Telescope battery, hydrogen batteries. They operate at really high pressures, but they generate hydrogen at that high pressure, and that allows them to store energy like a battery. They do have a really high self-discharge rate, but the benefit is that they last a very long time. These original batteries lasted 19 years on orbit before being replaced. And then I think they did eventually replace them with lithium batteries. But they definitely serve their purpose. So that was interesting. Those are the current applications, but they're exploring different applications for like generating oxygen on the moon. And this is where I'm going to talk about in my design, and I want to make a disclaimer here that I'm not trying to say that mine's the best by any sense of the imagination, especially in its current consumer form. I guess my goal is to just give an argument of how this design could work on the moon's surface, and I'm definitely not an expert on most of this. I learned a lot making this video, and I hope that you can get some of that from here. But yeah, this is my design for the electrolysis cell. Very simple. It only has a single moving part. And I'd also want to talk about my background a little bit. I have a background in satellite design. We did some satellite design for my university, but as I show here, I mean, I do a lot of stupid things that I feel level that out. So, I mean, everything cancels out, and I probably end up with an intelligence of 0 at the end of the day. But yeah, that's kind of my background. We did eventually launch this satellite, which I wanted to show here. So we launched aboard a Transporter 16 SpaceX rocket. So that was really interesting. And we were able to establish contact. So that was a huge milestone. But that's my background, I guess. I have a small background in as the electrical engineer on this project. But I wanted to talk more about this design. So a very simplified version of the cell is that it has 2 outputs. One is this center sealed off tube, and then this one has a check valve, and then this one is a solenoid that's normally closed. And this oxygen side generates oxygen, which eventually forces the water down and out of this tube, because this is just a check valve, so it can be overcome. So you have this high oxygen pressure pumping out the hydrogen effectively. And of course, you could switch the polarity on this and have the oxygen out here and the oxygen in the center being pumped out by the hydrogen. So it works either way. But eventually, you're going to get this water level too high, so it'll trigger and open the solenoid, which will reset the water level. And this process just repeats over and over. The oxygen pumps the hydrogen out, triggers a solenoid open, which vents the pressure and resets that water line. And eventually, the time that it takes to generate the pressure, enough pressure to force more hydrogen out, takes too long, which tells us that the pressure on the hydrogen side is too high and that we should shut down. So it's a very simple design, only needs one moving part and doesn't have any degrading parts. No like separating membranes or high temperatures involved, which is why I like the design. It was very simple and cheap to implement in a consumer product. But it does need gravity. So gravity needed. It wouldn't work aboard the ISS unless you build some centrifuge system like I showed up here. A system maybe like this would work. But we don't actually need that because we have 1/6 the Earth's gravity on the moon. So the bubbles generated would be a little bit larger than on Earth, and it would be slower to rise to the surface. But in general, the operation of the cell would be pretty similar on the moon's surface. And of course, I use that in relative terms. It would require a lot of testing. And currently, the PM cells are the favored ones aboard the ISS and everything. But I did want to compare like the 3 types. That one NASA paper mentioned that there was the solid oxide electrolyte cells, the the membrane electrolysis cells, and then they called the third category alkaline. But I mean, it's very simple. I mean, there's so many ways to design these cells. I discovered a few more variants while researching this video. So I mean, there's a lot of designs that would work with this. But I guess let's start with the solid oxide version. So the solid oxide cells operate at a very high temperature, between 700 and 1,000 degrees Celsius, and that's because they supplement some of the energy requirement for splitting water as this heat. They use steam over the anode and the cathode to improve efficiency. But the issue is that of course that high temperature leads to degradation faster, but also you get some like gaseous, you get some water vapor out on your hydrogen side, so you need to remove that with an external system. And just in general, these aren't, I don't see these deployed as much. I haven't seen as much evidence of them being deployed. So they just seem to be more difficult to get right. And I think the thermal cycling is a huge part of that. And then of course we're going to talk about the proton exchange membrane cells. So of course you have this membrane in between. And it looks like here you also have some water on the oxygen side as well. It's pretty unavoidable with these cells. I mean, you're going to get water vapor pretty much whether you like it or not, because you're getting the hydrogen and oxygen from water. So it's very difficult to get that out. But that's an example of a proton exchange membrane cell would be the electron aboard the ISS. And then of course my cell design is very similar to this diagram. I made this diagram that shows the reactions at the cathode and the anode. Very simple, basic electrolysis with sodium hydroxide as the electrolyte. So there's a separator in between here, and you get the hydrogen separated from the oxygen. Very simple, and in a safe design, you only have a single moving part. And then just a rigid separator that doesn't degrade like the membrane in the PM cells. But so now I want to talk about a little bit of the design comparison here. So in no order here, just in terms of cost, a lot of these estimates are really rough. But the solid oxide electrolyte cells, they range from that amount. My cells ended up being the cheapest, just because I use consumer materials. And it probably would be cheaper if you built one cell instead of 28, instead of requiring me to buy 28 pumps and 28 solenoids. I would only need one. So that would reduce costs if you built one cell. But of course, mine is designed with cost and mass production in mind. So it's not really space grade. I know from my work on the satellite project that a lot of these materials that I use are not allowed because of outgassing, especially epoxy and silicon. I would need space grade plastics, and especially to protect them from the heat if I want to be able to use these materials. So it'd likely require a redesign. And I mean, you can see here that the advanced oxygen generation assembly was part of this advanced exploration systems budget. And that budget was $123 million in 2026, or at least they're requesting that. So I think they can afford my $64 cell. So maybe that's not the best comparison to make here. But in terms of longevity, I mean, these solid oxide cells, they have a lot of thermal cycling. They have to operate at really high temperatures. So that could really harm their longevity. These proton exchange membrane cells have membrane degradation, less so with the more advanced ones. But I mean, I know that these electron cells were plagued with issues. So that just having that membrane in there is a possible point of failure. And of course, my cell suffers from a lot of the same issues with having a single moving part with the solenoid, which could fail. But just in general, it's a lot simpler. I mean, you have this silicon tube, which doesn't degrade over time. The nickel plates resist the sodium hydroxide environment really well. So there really isn't an issue with degradation in that regard. You're probably the biggest issue with these are thermal cycling on the epoxy seals that I have in here. But just in general, the amount of area you have to seal on my cell versus like a proton exchange membrane cell is night and day. I mean, you have all these sides to seal versus just a single part at the top, which isn't usually exposed to liquid. So the simplicity helps out a lot there. But in terms of output purity of the gases, I mean, you have with these solid oxide ones, you have steam on the output. Similar story with the PM cells, but I mean, it depends on the separator. You can get very high purity in the output. Probably the highest one here if you have a good separator. My cell, I firmly separate the two sides, but there is a bit of a gap here to allow for better conduction. So you could get some crossover if you move the cell too quickly. But that's very much worst case scenario. And of course, efficiency, they often, for the solid oxide ones, that's one of their main sell points is that they claim 80 to 90% max efficiency. But of course, that's when you have the heat to apply. And on the moon where it's pretty cold, you might not have that heat and you might have to waste energy warming the cell up. It's not easy to throttle these cells up and down. So that's why the PM cells are preferred, because I mean, while they have less efficiency in theory, it's much easier to throttle them up and down. And just in general, they don't suffer from the heating issues. And my cell, it's probably okay to assume that mine are not the best because I'm using hobbyist grade materials like nickel strip. I don't have platinum and gold in my cell like these other ones do, and I have a 5mm plate gap, which will increase resistance a little bit. So of course, moving on, what happens when we actually land on the surface? We have these 9 landing locations. We're not sure which one we're going to go to yet. We have these 2 rover lander possibilities. Excuse me. One from SpaceX, one from Blue Origin. One of those will touch down, but of course we're trying to deploy experiments, including getting oxygen and water, and possibly generating fuel. So I mean that'll involve a lot of different machines and things, and I did want to show some of that here. This is their video that they released of what the different things on the surface would look like. But they talk about deploying in situ resource utilization, all solar, battery storage, of course, to survive the nights there. They will have solar on posts. And then they also talk about how they're going to actually get energy down into these large crater regions where the water could be. Then they're thinking about beaming it down because the environment down there is so extreme. And of course, lunar dust is going to be a huge issue. They also talk about, of course, drilling, subsurface drilling. They talk about exploration of caves with different rovers. But in general, I mean, this is like 2 Antarcticas worth of cold down here. So the environment is very extreme, and they're not exactly sure how that's going to go yet. So I'd assume that if we get a permanent base, most of the resupplies would come from Earth, similar to the ISS. But I mean, they likely would want to make things more self-sufficient. So many of the things are still unclear, like how they're going to endure that negative 250 degrees Celsius, or how the rovers are going to get down into the craters, whether there's some more shallow craters or not. But I mean, yeah, you're going to have to make some specialized materials, like they're talking about like hybrid ceramic metal gearboxes to survive this massive temperature swing here. Because I mean, you have 50 degrees Celsius up here, and then negative 246 degrees Celsius down in the crater floor. So it's a huge temperature swing. They talk about getting this water out by just beaming energy down and evaporating it. I have some 3-point diagrams here, but a summary of that is that hydrogen liquefies at negative 250 degrees Celsius. So a little bit colder than these craters are. If you do pressurize it to 5 bar, though, you can get within this critical temp. So you could, if you're at 5 bar and you're at negative 246 degrees C, you could get liquefaction of hydrogen. So you could pressurize it a little bit and put it at the bottom of this crater. And they do show cryogenic storage here. And then oxygen is a little bit easier because it liquefies at a higher temperature. So you could just put it down here and that would naturally become liquid. But of course, this is all speculation on my part. It seems to me that you'd evaporate the water and then you transfer it, maybe you transfer it up to the warmer ring here, just because, of course, the astronauts need water. The electrolysis cells would operate better up here. You just wouldn't have to worry about stuff freezing solid. And then you might transfer it back down to the crater floor for the cryogenic storage shown here. But that's all speculation, of course. So I did want to lastly talk about what would fail first. Say we did get my cell to the moon somehow. You can tell it's a real image, Alan Bean holding my cell, because I mean you can see it in the reflection of his helmet. It's a very real image. But yeah, say it gets there. What fails first? Well, of course, with the cell being plastic, of course you got to worry about melting in the daytime temperatures. HDPE will start to soften at 100 degrees Celsius, but of course you don't want the water to be boiling at 100 degrees C. So just in general, like this high temperature is bad. But freezing might even be worse because it will expand and break the bottle. According to this phase diagram I found here, I mean, you'd get to freezing temperature. If I did an 18% concentration of sodium hydroxide in the water, it would start to freeze around 27, 28 degrees Celsius. So you need to keep it above that to avoid freezing. And electrolysis does produce some waste heat, so that might help a little bit. But in general, you'd probably want to keep the electrolysis cell in one of these crater rims where the temperatures are more moderate. Because at the crater rims, I mean, you could get temperatures that are around 50 to negative 50 degrees and swing. But even then, you might still get failure of epoxy seals over time just due to thermal degradation. And of course, UV light will lead to embrittlement of the HDPE. It's definitely something you want to protect the cell from. And the pressure differential is actually not much of a concern, as far as my research showed, because if you pressurize it on Earth, you'd have 1 atmosphere of pressure in the cell. The cell is completely sealed, so the bottle will survive that, no issue. And you would be able to operate the cell as normal, I feel like. But of course, that would need testing as well. But of course, 1/6 of the gravity doesn't make the cell operation too different. The bubbles would be slower, the bubbles would be a bit larger, but I mean, you could increase the surface roughness of the plates to help offset that. And of course, if I were to design this cell to survive in space, you would need a lot more thermal blocking. You would need to protect the cell from the sunlight, similar to how these lunar landers and how the James Webb had a lot of thermal protection. You'd probably need to have some layers of thermal protection. That's like the largest one. Well, of course, beyond replacing it with space-grade materials, you're just not allowed to have epoxy and some of these plastics and silicon for outgassing reasons. But number 2 is for sure the thermal insulation. And then I'd consider, not AI, but I'd consider aluminum or steel covering over the HDPE bottle. Maybe epoxy-coated steel on the inside. And that's mostly for like pressure and outgassing reasons. And then, of course, you might want to have like a proper check valve. In this design, I just have a bent tube, which does a good enough job at preventing outflows from the hydrogen side. But you want to have like a proper check valve to resist that 1 atmosphere differential if you fill it on Earth. And then, of course, you might want external control rather than the microcontroller setup I have here. You just need like 4 wires or so, one for sensing, well, 2 for power, 1 for sensing the water level when it touches the sensor, and then 1 to trigger the solenoid. So it's a very simple design. And then, of course, yeah, I mean, that's pretty much it. Of course, I probably missed something, so feel free to correct me in the comments. I'll try to pin any comments that point out things that I agree with, and for sure I'll make a follow-up video addressing concerns. I'd hope that this cell would work as intended on the surface, but of course I'm not an expert on any of this. And of course, if you want to support my future work, you could check out, if you want to play around with one of these cells, the link is in the description. But yeah, thanks for watching.